more participants. Okay, can you see my sharing?
Yes.
Okay, let's start. Hello, everyone. This is Chuanming Jia from Peking University and Pengcheng Laboratory. So in today's conference, we are going to introduce the latest activities and what is going on in the MPAI end-to-end video EEV project. So in this project, our objective is to learn the end-to-end optimized video codec so that this codec could be regarded as the future of the video coding community and show some potentials for some potential use cases. So at the beginning of this slide, I'm going to show you some literature review in the context of end-to-end video coding. So ever since the year of 2018 or 2019, so in the academic community, we have observed that there is an increasing research that is using the neural network models for the task of video coding. So we can categorize those methods into two different paradigms. The first one is the frame-based interpolation or extrapolation-based end-to-end video coding. Some representative work could be seen in some top conference venue in the computer vision, such as in 2018. There has been the first investigation using a frame interpolation for video compression. After that year, there has been it is an active research topic. We can see that some sort of bidirectional coding network, the 3D autoencoder with rate distortion optimization network, and something like the frame generation-based model. They have been published in some conference venue. And in 2020, we have observed that there is some sort of research work that use the bidirectional frame interpolation so that the interpretative coding can be realized using end-to-end trained models. So that is the first roadmap of this end-to-end video coding. The other one is some sort of methodology that is called hybrid framework end-to-end video coding. So the basic concept is similar to that of conventional hybrid coding framework. Such frameworks usually use the prediction plus transform-based codec, but the difference between the hybrid framework EEV and the conventional hybrid framework is that the hybrid framework EEV uses fully neural network models to realize prediction, transform, reconstruction, except for the arithmetic coding. So for that sort of methodology, the very first work we can find in the literature was a paper published in ReCeP 2017. It is called DeepCoder. And in 2018, some subsequent work tried to use this 3D convolution plus long short-term memory cell for the interprediction, so that the entire network can be overall and globally optimized. In 2019, there has been a very representative work called DVC, which is equal to deep learning-based video coding. So that paper has been a very solid baseline for the hybrid framework end-to-end video coding, because for that work, the entire module is realized using neural network and trained from end to end. So in the same year, we can observe that there has been some subjective quality-oriented optimization for the end-to-end video coding. And from that on until today, until this month, we observe that there has been more and more end-to-end video coding solutions, so that in my personal understanding, both the academic society and the industrial society have reached an agreement on that the end-to-end video might be some sort of technology which can be used for future video coding task. So that is the sort of literature review for our topic today. And let's go back to our group, MPAI end-to-end video. So the milestone or the timeline of this project is shown in this slide. So we officially kicked off this project on 3rd of November 2021. So it has been over an entire year since its official kickoff. So we have made several milestones and some achievements during the study. So at the very beginning of this project, we use a couple of months or a couple of weeks to write a working draft to know what is happening and what is the state of the art in the field of end-to-end video coding. So we have released such documents and in our website, and you can find such working draft in our website. And that literature review has covered what we have introduced in the previous slide. So at that time, we believe that one day we might realize a goal that the end-to-end optimized video coding model has better performances than the conventional state-of-the-art video codecs. And we meet the very first precise step at the end of 2021 because we received a donation from the author of OpenDVC, and the author has contributed this software as our starting point. So we labeled it as the first version of our reference model EEV 0.1. And the very first coding tool development in our project is to investigate the motion compensation network so that the predictive coding results are enhanced using such neural network. And moreover, we release the EEV 0.2 model by incorporating the motion compensation in prediction enhancement network for the on the top of OpenDVC, and we have observed significant. We have observed a significant the bitrate reduction by using the proposed motion compensation prediction enhancement network. And we use another 3 months to go further, and 2 more neural network models are investigated, and so that the coding efficiency is moved higher and higher. And that model is also released. Of course, you can request it by, you can find it upon request. So after that milestone, we move our coding content or our research topic from natural video to the drone video, because there has been an increasing demand, or there has been rarely investigated for such topic. So at the end of last year, we have released the drone video dataset, which will be described later in this talk. And by using this drone video dataset, we have tried several further investigations on the top of EEV 0.3. And in this February, exactly last month, and we have released our latest version of our model, EEV 0.2, I'm sorry, EEV 0.4. And this model has been made public available on the GitHub, and more details and documents are also provided in the MPAI EEV website. So you can easily find them free of charge and try the train, test, and evaluation code to seek further or potential investigations on your own end-to-end video codec. So that is the milestone of our MPAI EEV and what happened in the last couple of months. So this is, I believe that this project or this group is very productive, but we also observe that there is a lot of things that need to be improved. So in today's talk, it is free for the audience to interrupt me to have any further comments or questions. So let's move on to the very beginning of our story. So the starting point of MPAI EEV is the OpenDVC. So this is a model that is implemented by a doctoral student at ETH Zurich, and he has contributed his model to our group, and the technical report of this software can be found in the link below this slide. And the entire neural network based codec is shown in the right panel of this slide. So for the each picture, this software has established a neural motion estimation model, which is designed to find the pixel-wise optical flow between the current place-time image and the reference image. To ensure the encoder-decoder consistency, you need to compress or to send that motion field to the decoder side. So there is an image coder, end-to-end optimized image coder to compress such motion field. And at the decoder side, when you do the motion compensation, the software introduces a neural motion compensation module, and to generate the prediction frame, which is labeled as the XBAR-T here. So the subsequent operation is very similar to what is done in the conventional video codec. So you need to subtract the original picture to the prediction picture to obtain the residue picture. So the residue picture is compressed by another image coder, which is also end-to-end optimized, so that they can be perfectly reconstructed at the decoder side. So the critical problem in this entire framework is that the bit estimation, because you need to send two separate segments of bit stream, one for the motion field, the other one for the residue. So some prior knowledge or prior state-of-the-art model happened in the field of end-to-end image coding is borrowed, so that the entire network can be implemented and trained from the input to the reconstruction. So this work is this model is end-to-end trained, and this network is the network shown here is the motion estimation module. So it is somehow a pyramid-based flow net, and this is very typical model in the task of video processing in the computer vision community. So experts with some prior knowledge in deep learning might be very familiar with that module. So based on the viewpoint of 2023, the entire framework is easy to catch and easy to understand. But if you stand your foot on the year of in the year of 2018, you will find out that it is not an easy task to build such framework and to train them and to find a proper performance. But luckily, this is our starting point, and there is no other intellectual property risk or other non-technical issue. So this has been our solid baseline. So this model is also public available, so you can try it and regard it as a baseline. So regarding the performance in the original paper and the technical report of the OpenDVC, we can observe that the bitrate reduction or the BD rate performance on the JCTVC test sequences. So the OpenDVC has similar or comparable performance with respect to the X265 video codec, which is implemented by the FFmpeg using the very fast preset. So actually the H.264 and H.265 baseline here is a very, how to say, very weak baseline, because they are not implemented by the reference software by the standardization group. However, this work is regarded as the starting point or as the beginning of the neural network-based video codec. So at least this work has shown the potentials that the learned codec at least can be comparable with some conventional standard using some specific test conditions. So that is the where this end-to-end video codec originates. So although the performance is not good enough at that time, we still have received some sort of confidence encouraged by this work. So let's go back to the EEV model development. So in EEV research or in EEV study, we do not emphasize our model on the natural video compression because we believe that some other standards such as VVC, such as AV1, such as AVS, they has been quite well done in the task of natural video compression. So to seek something with a sort of academic novelty, the EEV project focus its eyes on the drone video. So the first thing is to build the drone video benchmark, including the testing sequences. So the 14 cherry-picked video clips are selected as the testing benchmark, and they are representative because, as you can see, the basketball ground, they have large areas of color textures, and the height of this drone devices is not very large, so that the object within this picture is sort of close to what it should be in the natural videos. So this is a very interesting test clip that has provided some sort of another viewpoint to the natural content. And regarding this, the second test sequence, as you can see, some air conditions are different from what it actually happened in the daylight, so that the drone videos may capture some noise during its imaging. And also we have some pedestrians in this texture, so that if you do some specific if you do some specific coding tool design, maybe those pedestrians are damaged. And I will not describe those sequences one by one, but as you can see, the particular or specific types of video content are selected, especially for this class of clips, because this is those videos are captured by the indoor drones, so that the indoor drones have some specific lens distortion, which is called fisheye distortion. So that sort of distortion is not captured by the latest coding standard, and we have also we will also show some simulation results in our later in our talk. And another interesting thing is that in our benchmark, our videos have different height, so that the object or the shape of the object are different because the imaging condition by the drone video. So that would be very interesting to see what will happen in the end-to-end video codec and the learned and the conventional video codec. So in this picture or in this table, we have depicted the statistics of this 16 drone clips. So the largest resolution of them is over 2K, and the smallest one are somehow 600 by 300, and they are all standard dynamic range because we did not have any device with HDR imaging on the drone devices. So this table has been published. Actually, this has been part of our EEV project paper, which will be presented in the data compression conference this year. And more details will be found in our official website, so that you can see the more details of our data set. So here we depict the reference model development after the starting point, and what we have realized in the three major version of our reference model. So for the EEV 0.2, as you can see, we just incorporated the prediction enhancement module within that, and in its in its successor, and we have introduced more deep learning based coding tool, such as the two-stage residue codec, and the restoration network, and also the entire network is trained end-to-end. So in our latest module, which has been published in this venue, and we have tried some further investigations by using some deep feature space interprediction, as well as something like the deep motion modeling for the learned video compression. So the prior knowledge that has been investigated, such as the in-loop filter or the restoration and the prediction refinement, are also implemented within our framework. So the entire framework is has better performances than what has happened in the EEV 0.2 and EEV 0.3. So let me just give a quick overview of our reference model 0.4. And for the reference picture, we firstly borrow them from the decoded picture buffer. Then we just using some sort of feature embedding network, and this is an encoder-like neural network. And the functionality of this module is to map the reference pixels into the deep feature space. So for different video pictures, we embed them into different deep feature embeddings. Then we employ the residue-based long short-term memory module, and we model the motion field and the motion dynamics using the residue LSTM module, so that we can obtain some sort of coarse prediction. And to realize some fine gradient prediction, one thing we need to do is to signal some information from the encoder side. So our design is to concatenate the current pre-time image and the reference picture together, and use some motion extraction encoder and the decoder structure, and send that information to the decoder, so that some fine gradient or further information which can be used to represent the motion is signaled to the decoder. So the entire operation is done in the deep feature space, so that we cannot regard it as some sort of pixel-wise operation, just like what happened in the conventional video codec. And before we really obtain the predictive interprediction signal, one thing we need to do is to transform them from the deep feature space to the pixel space. So we design a symmetric module, which means that the feature embedding and the feature restoration are symmetric. So it is some sort of decoder-like network, so that the x dot t frame here is the first stage coarse prediction frame. And we also apply the interprediction refinement network to that predictive frame. I should point it out that at this stage, the entire operation is done in the pixel domain, so that the inter-refinement is exactly enhance the quality of the interprediction. So this is the knowledge that we have investigated in the previous two version of our reference model. So finally, you can got this prediction frame here, and naturally you will send the predictive residue to the prediction decoder, encoder, and to the residue encoder and decoder, and which is followed by the loop filter after the reconstruction. So that is the major module of our EEV reference software for its latest version. So the dash blocks are some encoder-only block, and the bold blocks are the decoder-side block. And as you can see, the reason for calling it a decomposed motion lies in that our motion is represented in two parts. The first part is the intrinsic motion, which is exactly learned from the reference pictures borrowed from the DPB. And the other part is the compensatory motion, which contains some sort of original information at the encoder side, and they are compressed and sent to the decoder so that they can compensate some fine-grained motion that is not captured by the residual LSTM when you only use the reference pictures. By doing so, we just make some imitation operation with the advanced motion vector prediction in the conventional codec like VVC and HEVC. And by this design, our motion representation efficiency is much higher. So that is the detailed description of our EEV reference model development. And in the subsequent slide, I will dive into that software and introduce more interesting results. So regarding the EEV 0.3, we have tested our results with the with some standard codec, and our starting point OpenDVC, which is labeled as EEV-0.1. So our test condition is listed here. We employ the HEVC reference software with screen content extension, so that our test condition can be aligned, because the neural network-based codec are in the RGB domain for the processing, including the train and test. So we also encode our clips using the HEVC SCC model in the RGB space. And the intra-period number is set to be 16 for all comparisons, so that we believe that the test is reliable and is persuasive enough. So regarding the table in the left panel, you can see that the EEV has obtained a significant performance improvement when you compare it with the OpenDVC. And so this is a very successful investigation for EEV, because on average, 20% of coding gain is realized by introducing 3 more learned video coding tools on the top of OpenDVC. So another interesting thing is that in the last column of this table, if you compare EEV with HEVC, on average, you will observe a significant loss when you compare that learned codec to the conventional codec. But if you just only look at the class A, B, and D, which is the outdoor scenes, and the learned codec has significant performance improvement against the HEVC. The disaster happened in the indoor scenes, and the reason has been analyzed in our previous conference, in our previous meetings. Sorry, and we believe that the learned codec currently cannot handle very well for those contents with fisheye distortion. So that would be interesting to see if we use further fine-tuning using similar data set, whether it would be better for the EEV. So that is our undergoing operations, and we believe that in our future discussion we can show more evidence on that such point. And in the right panel of the slide, we show the rate distortion curves. So the pink curve represent the RD efficiency of EEV. So the sub-figure A, B, and C represents different video clips from the outdoor scenes, and the last sub-figure represents the compression efficiency among the elevator sequence, which is an indoor scene. So this behavior, the rate distortion curves behavior has corresponded to what we have observed in this table, so that for the EEV 0.3, we can conclude that the learned codec has shown some potentials to outperform the conventional codec, but in some specific content, there still need further investigations. So that is for the performance comparison in EEV 0.3. And we also release this technical report as our in the archive, and you can find the link in our website, in our MPAI EEV website, to see more discussions and some details. So that's something about our previous version 0.3, and in this slide I will introduce our latest performance on the 0.4. And so this page has shown a lot of information, and I will introduce them one by one. So we show the MS-SSIM based rate distortion curve in this here, and we compare our latest software and with the VTM software 15.2, and the VTM software is using the common test condition of low delay B configuration. So the red curve here shows here indicates that our latest reference software EEV 0.4 has reached its highest performance among other codecs, including a learned codec, DCVC, MVC, FVC, and other. And moreover, it has also shown the higher performance than conventional codec, such as X264, X265, and VTM. And I should point it out that the X264 and X265 are implemented using the FFmpeg with very slow preset. And I should also point it out that the VTM is not optimized for the MS-SSIM. So some experts from the external affiliations has suggested that we can compare our model with the VTM with optimization for the MS-SSIM. So that is also under construction. So we are also expected that comparison. But anyway, we believe that in current results, it is very encouraging for this group and for our learned video codec research, because as you can see, we observed that our model, as well as some some second best leading solutions, have realized better performances than the latest standard VVC in terms of the low delay B configuration. And the interesting thing is that as we have described in the previous slide, the EEV is using some sort of coding structure like a low delay P frame, because we only use a single direction of a prediction. But the RTM is configured by the low delay B. So this is also shows the efficiency of the learned codec. And that is the analysis of this rate distortion curve. So I believe that the following table will be more informative because in this table, we set the X265 as the anchor with a very slow preset. And we test many video codecs using the diverse test contents, such as class B to class E, and the MCR GCV dataset, and the UVG dataset, which is of a high frame rate, which the FPS is 120. And by analyzing them, we can find out that our model has shown the highest performance, and we label the highest performance using the red color, the second best as the blue one. So as you can see, when you use the MSSSIM as the distortion metric, we observe a very powerful performance over the X265. On average, about 15% is bitrate reduction is realized. Of course, you can observe that the VTM is also very powerful, especially for class E. But our label is our comparison is made between the neural network-based codec, so that as you can see, on average, our model has better performances than VTM. But when it comes to the PSNR as the distortion metric, we might be not that optimistic, because we find out that the VTM is absolutely the champion among all the candidates. So we just take it, leave it aside, and we compare other learned video codecs. So as you can see, our performance is we can just regard our model as the state-of-the-art, because in some sequences, maybe some recent publication like DCVC and FVC have higher efficiency, but on average, our model obtains the highest performance by the aligned test conditions. So another interesting set of experiments is shown in this table in the right panel of the slide. And we also use the MSSSIM as our distortion metric. So among the 14 indoor sim and outdoor sim drone video clips, we realize on average over 6% of coding rate reduction against the VVC. So I believe that this has been a giant leap between the 0.3 to the 0.4, because in the last version, we are still inferior to the GVC, but in our latest model, we can compete with the VVC in terms of the MSSSIM. So we just omit the PSNR-based metric because there has been a long way to go. So that it would be our future direction, because we all know that it is not easy to outperform the VTM using the MSE as the optimization objective. So here we show some subjective quality. This picture has been shown in the last MPAI EEV conference, but I want to call it back because this has been very encouraging in terms of the visual quality comparison. So in the top row of this visual quality, I believe that the standard experts are very familiar with this sequence. They are the blowing bubbles, and so as you can see for the texture here, which is coded by VVC, that is blurry, and the quality is a disaster actually. But in our model, we can very perfectly restore that content, especially when you're comparing with those texture against to the original ones. And for the bottom row of this slide, and this slide is of high definition resolution, which is picture from Kimono. And when you take a close look at the clothes of this female, and you can see that the texture is blurry, and sometimes you have observe some artifact here. But if you compare with these two sets of reconstruction results, and our performance is significantly better and clear to restore this texture, and it is very similar to the original content. And I should note that both of this content is optimized for the MSE, and the quantization parameter for the VVC is the QP value is 35. So we just equal the lambda, which is the trade-off between the bitrate and the distortion, and we set them to be 8. So I think the above content are some major introduction to what we have realized in the MPAI EEV project and what we have achieved for our research in the past several months. And for the future study, we are going to seek some future use cases because we all know that in our learned video codec, the only thing that you want to signal is the motion and the residue, and so that they are all represented in the deep feature space. So for the future use cases, the learned codec might support some compressed domain analysis without retraining or without decoding. So that would be a strength or a plus when you compare the learned codec against the conventional codec. And another future use cases is that if we do not want to use some standardized codec, we're just using some private protocols for this software or hardware-based encoding and decoding, the learned codec might be a choice, especially for some long-term storage use cases, which are some contents that might be stored for years or for decades that are not need to be decoded. So that it would be might be very interesting use cases. And we have received some inquiries about the complexity or the operation number of our reference model. So we just make some statistics of our latest 2 version of our software. So for the EEV 0.3, we need 7.7 T flops for each bitrate point compression. Oh, I'm sorry, I missed a 0 here. It should be 50 million parameters for each bitrate point model. So the same number for EEV-0.4 is 5.4 T flops and 23 million parameters. So I believe that there are a lot of parameters when you're comparing the neural network codec against the VVC codec or the HEVC codec. But if you use some powerful neuron processing devices or edge computing devices, that would be resolved the computational cost. But it is an open discussion problem because we are not the hardware expert. We do not have some in-depth prior knowledge or domain knowledge in such design. So we are expecting more contributions to those related issues. So I think that's all about what we are going to talk today. So it's welcome to visit the MPAI EEV official website, because you can you can find many interesting things that has been posted by the secretary of our community. So and the chair of our MPAI group. So I think today I'm going to end my talk here, and I expect more discussions and comments on our work. Thank you.